Kylo Limit Loren, back talking to you about the squeeze theorem. What did Obi-Wan tell Luke when he didn't know how to use chopsticks? Use the fork, Luke!
First thing we're going to talk about is the squeeze theorem. That says if h of x is less than or equal to f of x, which is less than or equal to g of x for all x in an open interval containing c, except possibly at c itself, and if the limit as x approaches c of h of x is equal to L, which is equal to the limit as x approaches c of g of x, then the limit as x approaches c of f of x exists and is equal to L. It makes sense in that if h of x is the smallest function, f of x is the middle function, and g of x is the greatest function, and if at some point we know that the limit as x approaches c, some x value, for our h of x, that limit equals L. And then the limit as x approaches c for g of x also equals L. Then it follows that the limit as x approaches c for f of x would also have to equal L, because it's right smack dab in the middle of those two functions. That's why it's called the squeeze theorem or the sandwich theorem, because f of x is sandwiched between h of x and g of x, and if these two have a limit as x approaches c equal to L, then this one must also have a limit as x approaches c equal to L. Now I have kindly included a nice little turkey sandwich down here to help you remember that the squeeze theorem is also called the sandwich theorem. We have turkey in the middle with some beefsteak, tomatoes here, lettuce on both sides of the meat. That's kind of crazy, but whatever. The squeeze theorem graphically looks like this. We have our inequality where h of x, the lesser function, is less than or equal to f of x, our middle function, which is less than or equal to g of x, our greater function. Now, if we look at the limits, part 2 of the squeeze theorem, we know that the limit as x approaches c of h of x, our lesser function, must equal L. So as x approaches c from the left and the right on h of x, we have a y value of L. Therefore, the limit as x approaches c of h of x is equal to L. If we look at our greater function, the limit as x approaches c of g of x, so as x approaches c for g of x, we can see that they both approach a y value of L as well. Since f of x is between h of x and g of x, we know that the limit as x approaches c of f of x must also be equal to L. So as x approaches c of f of x, you can see that the limit must also be equal to L as well.
Help me, Obi-Wan Kenobi, you're my only hope! I'm your only hope now! It's example time!
Now example 1 says use the squeeze theorem to find the limit as x approaches c of f of x. So when we solve squeeze theorem problems, there's 3 things that you need. The first is you need to write the inequality that we're using. So the good thing about this problem is that it gives you the inequality. So all you have to do is just rewrite this inequality. We have our lesser function, we have our middle function, and we have our greater function. Perfect. Next, we need the limits of our lesser and greater functions. So let's do that. The limit as x approaches c, which in this case is 0, for our lesser and greater functions look like this. And to evaluate, all we do is plug in 0 for our x and solve. So we plug in 0 for x here and simplify, and we end up getting that the limit as x approaches 0 of our lesser function is equal to 8. For this one down here, the limit as x approaches 0 of our greater function, we again plug in 0 for x, and we get 8 as well. Then, the last step, you're going to write, therefore, the limit as x approaches 0 of f of x, our middle function, has to be equal to 8 by the squeeze theorem. And it makes sense, right? If our limit as x approaches 0 of our lesser function equals 8, and the limit as x approaches 0 of our greater function equals 8, and f of x is between those two functions, the limit as x approaches 0 of f of x must also be equal to 8, and that is by the squeeze theorem. Part B, doing the same thing. Again, it's a squeeze theorem problem, so what we do is we write our inequality first. And again, it gives us our inequality. Done. Next, we need to find the limits of our lesser and greater functions. So we find the limit as x approaches our c value, which in this case is m. So this is going to be kind of weird because it's more algebraic than numeric. So what we do is we take m and we plug it in for x. That's how we solve our limits analytically. So we're going to take this m, plug it in for x, and find the limit as x approaches c of our lesser function. So when we plug that in, m minus m gives you 0, and the absolute value of 0 is still 0. P minus 0 then is just p. Here, also for our greater function, we plug in m for x, we simplify, and we end up getting p as well. Since the limit as x approaches m for our lesser and greater functions both equal p, then the function in between those two functions, f of x, must also have a limit as x approaches m equal to p. So we write therefore, that's the third part of our squeeze theorem. The limit as x approaches m of f of x must equal p by the squeeze theorem. Inequality, limits of the outer functions, then therefore.
Anakin was not the chosen one. I was. You try.
Okay, so here we're doing the same thing. We start with our inequality. They give us the inequality, perfect. Rewrite it, done. Next, we find the limits of the lesser and greater functions. So first, we are finding the limit as x approaches c, which in this case is 0. So we find the limit as x approaches 0 of our lesser function and our greater function. So here, to evaluate the limit analytically, we plug in 0 for x, we simplify, and we end up getting 5. For our greater function, when we find the limit as x approaches 0, we again plug in 0 for x, simplify, and get 5. We then write therefore, the limit as x approaches 0 of g of x, our middle function, must also equal 5 by the squeeze theorem. Part B, we're doing the same thing. Inequality. Start with what we're given, done. Next, the limits of our lesser and greater functions. So the limit as x approaches 0, which is our c in this case, of negative absolute value of x, and the limit as x approaches 0 of positive absolute value of x. So to evaluate these, again, we plug in 0 for x, we simplify, we end up getting 0 for our lesser function, and then for the limit as x approaches 0 of our greater function, we again get 0. Because these are the same, we know that the limit as x approaches 0 of our middle function, h of x, must also equal 0 by the squeeze theorem. Now example 2 says use a graphing utility to graph the given function and the equation y equals absolute value of x and y equals negative absolute value of x in the same viewing window. Using the graphs to observe the squeeze theorem visually, find the limit as x approaches 0. So all this is asking you to do is graph y is equal to absolute value of x and y is equal to the negative absolute value of x in a graphing calculator. You then graph our f of x, our function, absolute value of x times sine of x. So here we have y is equal to the absolute value of x up here, y is equal to the negative absolute value of x down here, and y is equal to the absolute value of sine of x in here. Now, it wants us to find the limit as x approaches 0 of our function right here using this graph. And that's pretty easy because we have our upper function, our lower function, and our function in the middle, which is f of x. The limit as x approaches 0 of our greater function up here, y is equal to the absolute value of x. You can see as x approaches 0, it also has a y value of 0. It approaches a y value of 0 from both sides. Same thing down here. The limit as x approaches 0 for our lesser function, the negative absolute value of x, also is equal to 0. Therefore, since the absolute value of sine of x is between those two functions, you can say that the limit as x approaches 0 of f of x, our function right here, must also be equal to 0. Now, if we wanted to do this analytically, I can show you how to do that. Again, we need an inequality. To figure out our inequality, we need to eventually have our function right here in between negative absolute value of x and positive absolute value of x. Well, we know that sine of x bounces back and forth between 1 and negative 1. So we can say that negative 1 is less than or equal to sine of x, which is less than or equal to 1. We could then just multiply each of these by the absolute value of x, and we have our inequality. The negative absolute value of x is less than or equal to absolute value of x times sine of x, which is less than or equal to absolute value of x. There's our inequality. Now all we have to do is find the limits of our lower and upper functions. So we do that. If we were to evaluate this, all we do is plug in 0 for x and simplify, plug in 0 for x and simplify. Because the limit as x approaches 0 of our lower and upper functions both equal 0, we can say, therefore, the limit as x approaches 0 of our function must also be equal to 0 by the squeeze theorem.
Do or do not. There is no try. Except for this, you try.
Okay, so this time we're doing the same thing, except this time our function, f of x, is equal to x times cosine of 1 over x. So we graph the function y is equal to the absolute value of x, we graph the function y is equal to the negative absolute value of x, and we graph our function f of x. We do this and we see that y is equal to absolute value of x is our upper function, y is equal to negative absolute value of x is our lower function, and our function f of x is between those two functions. Because it's between those two functions, we can apply the squeeze theorem to the limit as x approaches 0 of our particular function. Since we know that the limit as x approaches 0 for absolute value of x equals 0, and the limit as x approaches 0 for negative absolute value of x also equals 0, then we can infer that the limit as x approaches 0 for our function also equals 0. Now, if we wanted to do this analytically, we need an inequality, and you see that our function x times cosine of 1 over x is between these two functions. So we can set up our limit that way. We then can write our limits for our lower and upper functions as x approaches 0. We evaluate those by plugging in 0 for x here and here. And when we do that, we find that the limit as x approaches 0 of our lower and upper functions both equal 0 as x approaches 0. We then write, therefore, the limit as x approaches 0 of our function must equal 0 by the squeeze theorem.